This is working. This was a very interesting day of talks, and thank you for the workshop organizers for bringing together all of these great set of speakers. I'm super glad that I get to speak to all of you. I am a little disappointed that I'm not there in person. It would have been a lot more fun, but hopefully, what I'm going to talk about will lead to some food for thought. Of course, I will be available for questions online after this. Feel free to send me an email and everything. So let's get started, right? I've been thinking about this idea of doing planning or embodied planning. And over the last few years, I have arrived at this framework that looks very similar to what we these days call agentic AI. And I'll give you a glimpse of what we have been doing in this space. Of course, we haven't solved all the problems, but we believe that these ideas form the basis of what a general purpose planning system might look like. Very similar to uh, Chu Chu and the group who just presented, and their line of work has been very interesting. So, according to me, before we even talk about what can LLMs do or what can LLM do for robotics or foundation models do for robotics, one way to really think about this problem is understanding what are foundation models good at and what are foundation models not necessarily good at today. Generally, foundation models, by the nature of the data they have been trained on, are likely going to be good at what you would call the what of the problem. You tell me, open the door. It can tell you what it means to open the door, the reasoning and the common sense, right? Effectively, they can ground the concept of what needs to happen. Maybe can create an abstract plan, but really, they cannot create what you would call a solution for a robot. That happens with what you would call a different model. Let's call that a how model. Basically, someone tells you the concept of opening a door. So now that you know how the door opens, you still need to figure out how you will solve this problem for your own self, if you will. And this is what I would call self-aware motor control because it's morphology aware. Different morphologies will achieve different policies, right? Uh, and notice that this is not system one, system two breakdown. Both models can be system one or system two, both. The breakdown is in a different dimension of understanding the grounding part and figuring out the solution. In control perspective, this would be the equivalent of saying the what model is a reference generator and the how model is a reference tracker. Okay, so with that in mind, I think that helps us use the idea of what foundation models can do for planning. One way to think about planning can be, in a lot of cases, when we think about planning, particularly in robotics, what we do is the low-level skills are simple. Sometimes they are pick and place, sometimes they are pre-coded, sometimes they are stochastic, but they are almost, let's say, assumed to succeed. Majority of the complexity is in terms of the plan being complex. Within this space, you can say that skills are given, but planning domain is not given. So you have to figure out how to do it. That is why the problem is hard. Or you are asked to learn the skills alongside planning. That makes the problem equally hard, or if not harder. But there is a different aspect of the world as well, especially in robotics, where the skills are complex, but the plans are simple. Meaning the concept of opening a jar from a planning perspective is straightforward. The plan is almost always the same. It's the low level skills, the rubber meets the road, where things break down, right? So in this case, you can imagine that plan is given, but it fails upon contact. Contact meaning the rubber meets the road, not necessarily contact conditioning. Uh, and then how do we train or create these foundation model level skills without foundation model training data, right? So let's get started. The first thing we have been thinking about is this idea that we don't want to specify planning domains because that is exactly the problem that is very intensive. In this case, let's assume skills are given. So this idea that we can use program synthesis as reasoning and planning abstractions is something that is not new, and And I'm glad that people across the community have sort of converged to this, both within robotics and even outside robotics. We have been looking at this idea that we can do program synthesis effectively as planning domains directly, where the program output could be a skill or a full program. We did some work called neural task programming, neural task graphs, where the planner or the foundation model was an RNN, which was the best model at the time. Then we did proc prompt and clarify 2 years ago, which were concurrent with Code's policies and SECAN. And then recently we applied this idea to more complex, long-term, let's say hour-long programs as well for chemistry robotics. But in all of these cases, I think we were using what I would call the model as the planner, right? So there is no way for it to solve general purpose problems because the model effectively, it doesn't matter what the model is not a general purpose computer. It can do good pattern matching, it can do very good warm starts, but it will not necessarily solve any arbitrary planning problem. Which basically brings us to the idea that if that is the case, then what can we do where it's kind of best of both worlds, where we can capture this long tail of a problem. There will always be some new problem that a planner or a model cannot solve zero shot. So the idea was, can we, instead of making the model learn plans, output effectively the planning domain itself, right? And then the planning domain can be PDDL or signal temporal logic. It depends on how you want to define your domain. But you could argue that any domain is effectively a DSL. PDDL is just one idea. You can train these models on multiple setups. And the most important part is, in this case, you're asking the model to increasingly add complexity in these domains. How would something like that work? It is fairly easy. You can basically say, initially, I start with a single module. Often, a single task in a particular domain can be simple. You might say, okay, I have some state, perception can be converted into logical states using, again, pre-trained foundation models. You are given some set of skills, you generate some domain knowledge, and then you create a task plan. Now, the interesting thing is, if you want to add a skill, you can, in principle, in case, let's say, this particular pre-specified set is not sufficient, and that is something that the model will tell you when it needs. And as you keep going on, you can basically say that I can keep adding new tasks. The important thing is, effectively, you are building what you would call, in this case, a world model. The world model is not really the model of dynamics, but the domain definition. And you can do this in a manner that is what you would call continual learning, right? So effectively, language comes in, uh, some sort of PDDL model comes out. The important part that comes out is grounding, because the grounding is the part that is very hard. In almost any sort of definitional uh, domain definition, these grounding are effectively classifiers, and you need to specify classifiers. And this is the thing that you need to generate. So we are generating code in this case, but the code is for predicate grounding. And then you can use planners as you want. And because you're using a certain type of planner, you can also use verifiers and so on. But the important thing is, if the plan fails, you know what needs to be corrected in the model. And you can use this process to iteratively improve the model and the grounding system. Notice that in this case, the verification is actually happening from the planner itself. So that is an external system. So it's not a zero-shot self-evaluation system, which would not necessarily succeed, right? So you can start out with simple domains. Let's say, oh, do A and B, and then it turns out that, oh, in this case, it learns that if you want to pick up B and stack between, but the concept of between hasn't really been clearly specified, so it needs to be corrected. And then once you correct it, now the model can actually be a little more what you would call precise, because then this precision is necessary for this task, right? And this was just a very simple example. You can keep on adding task complexity, and what we see is effectively zero-shot models start failing, while this model, which is accruing model knowledge or world knowledge, uh, succeeds even as task complexity grows without needing additional data. This is the core, if you will, takeaway, right? So effectively, what you're doing is you're building incremental world model which allows you to do reasoning with. Now, this world model can be thought of as an explicit memory. In this case, it's an explicit world model that allows you to do verifiable planning. Now, let's assume that skills are also supposed to be learned while you are doing planning. So you're not really given anything, right? So in this case, high-level reasoning and low-level planning needs to be done simultaneously, but you're not given a lot of priors. In this case, what we do is we actually do code generation at the low level, but we do code generation in the sense of reward models that can then be used either in control theoretic approaches to do motion generation or reinforcement learning for skills. So now what you have is effectively a high-level planner that wouldn't work, while replan basically predicts a high level plan that in turn predicts a smaller plan, and then at the lowest level it is predicting a reward model. So it's a this I would call is akin to an agentic system which makes different calls to different models in different contexts, and is breaking down the problem from a higher level to a lower level in a manner that is automatic, right? Without getting into details for the lack of time, what I would show you is what kind of problems it allows you to solve without the need for pre-specifying common sense. So in this case, the task is fairly simple. The task is put the block in the cabinet. But now we don't tell the system that the cabinet is not openable. There is something there that would like block the cabinet. And this is what the system discovers. It basically creates a plan which says, pick up the cube and go to the wooden cabinet and open the cabinet. But then obviously you cannot open the cabinet because it was blocked. So now you have to replan and say, okay, now move the block outside or unblock the ability to open the cabinet so that you can move the block inside, right? So you are doing this sort of reasoning. You can have semantic constraints as well. So you're basically saying find a green apple, but you didn't say where. So you're asking it to do exploration. So in this case, it says that look inside the cabinet, grab the green apple. You basically say look in the cabinet, green apple not there, done, right? So you can now replan, look elsewhere, right? Uh, Maybe you need to look in the microwave, but the microwave is not openable. So you need to be able to do this. The important thing is, in this case, all of this planning and reasoning is happening in an end-to-end manner without us defining anything either in the domain or defining anything from a reasoning perspective. The system is automatically saying what could reasonable plans be given the set of objects, right? And then you can do interesting semantics as well. So in this case, the semantics is uh, open the stone cabinet. The weight sensor lock can be unlocked by putting a red cube on it. So now you're looking for a red cube first. Uh, then you have to figure out where the red cube will go. So the red cube needs to go effectively on that green plate. When the red cube is on that green plate, only then is the stone cabinet unlocked. Otherwise, you can't open the stone cabinet. This is very similar to you have to tap your ID to get inside the building to unlock the door, right? Uh, so this sort of reasoning with semantic constraints and exploration is something that now we can do with these planning-based systems, which was earlier not very easily possible, primarily because either the domain definition didn't exist or it was very hard to build. Uh, and in terms of timing, of course, you can do this nearly zero shot without training, except that the structure of the agentic model needs to be specific. So if you do not do replanning, the system doesn't really work. You still need perceiver, which means a very good visual feedback needs to be existing. You need a verifier, which allows you to ensure that the plan can work. And then effectively the whole thing is much better than almost everything that we have seen so far in terms of planning with these sort of systems. And at the time when it came out, uh, I think it was also better than almost every language to reward paper uh, uh, and zero-shot reasoning methods, including GPT-4, right? I don't know how much time I might have. I'm the only thing standing between you and lunch. Maybe I'll try to wrap this up in 5 minutes. So moving on and flipping around the question where, okay, planning is hard, but sometimes planning is possible and still robotics isn't solved. And often what happens in those cases is the planner may work, but the low level things or creating those low level skills, it just doesn't exist. You can't do it, right? A very good example was task and motion planning, which requires a lot of contact conditioning tasks. So a good example might be, let's say you have to create coffee. So to actually make coffee, whether in simulation or reality, there will be times where you actually have to do very complex contact rich manipulation. Usually, those are the kind of skills that are very hard to pre-program, especially if you're using a TAMP style mod. So you might be able to create skills for with motion planning. You might be able to create some skills with behavior cloning. Uh, and what might happen is there are different types of subsets of motion that might require different types of skills. In some cases, you might create a skill with teleoperation. And then our argument was instead of doing pure teleoperation where we do not achieve generalization, we can actually do very little teleoperation and RL-based fine-tuning. So in this case, the video is such where you're seeing that every time the border is red is a reinforcement learned skill, and every time the border is non-existent is a motion planning based motion generator. So in this case, what you're really seeing is a system which can do complex multi-stage tasks, which includes contact, and in these cases, the amount of data needed for training each of these contact-rich skills was very small. The BC initialization was close to 20% success rate, or sometimes even lower, while the final model achieved 99% success rate on most of these subsets of skills. So uh, this framework of RL-based fine-tuning of skills, but specifically in places where you need them, reaches 80% in most of the tasks, while solutions that are either task planning, behavior cloning, or pure RL don't solve them. And then the quality of the solution itself is also better. It's faster, right? Uh, and then most importantly, the system achieves robustness with far less data. So behavior cloning needs 200 plus demonstrations on every subskill, while this system can start with only 10 or fewer demonstrations and fine tune them into a very high quality performance. Right. So it improves times to completion, and then it also results in, let's say, stable, long-term, long horizon tasks. Right. I do not know how much time I would have. I would like to bring this to a close without taking too much of your time, and I'll just give you one more video without getting into details. Happy to chat more about this. There's one big problem that we have been often in task planning or planning in general, pushing under the rug, which has been the idea that perception we have just assumed to be solved. So for a lot of perception in robotics, we assume that either it's solved or we have a very simple mechanism of solving it broadly. Turns out that actually it is surprisingly non-trivial to do. Even simple things like putting a wire into a socket, standard models don't actually do it. They can tell you it can go here, but they cannot actually solve the problem for you generally, right? Or there are a variety of tasks, variety of objects, and so on. So this is one thing where we did where the question we're asking is what can we do so that we can place objects? So it's a place skill, but generally any object anywhere kind of thing. Uh, so the idea is very simple that a pre-trained VLM is very good at high-level semantics. So it can tell you, okay, I want to put the while in the while rack. So it can tell you possible locations, but it cannot actually tell you poses. So it's where the rubber meets the road where foundation models fail for robotics, the low-level part. These are things that don't work. So Malmo is the best open source model for 3D point prediction in space, and seemingly even that didn't do the trick. So that basically tells us that we have to build a new model which now solves the part where placement or post prediction can actually be, let's say, posed as a point cloud matching problem. Uh, if you do this at a large scale with simulated objects, you can train a single model that achieves very good generalization. So now, effectively, you are using best of both worlds in a sense. You're solving problems that off-the-shelf VLMs cannot do. In fact, fine-tuned VLMs cannot do. Uh, this is a mechanism to solve problems that are useful and practical for robotics. And mind you, none of the robot data, training data, was any of the things that you're seeing. And importantly, all of the training data was purely in sim. So this is another result in the sense that you can actually achieve general purpose systems or foundation model style generalization without the need for foundation model scale data. And whatever data you need can actually be generated purely in simulation, which is very much within the capability of smaller institutions, smaller compute, and even academia, right? With that, I would like to bring this to a close. If there's anything that you please take away from this chat is the idea of using program synthesis, either directly in domains or, as Chushu pointed out, directly as programs, is a very powerful idea for planning. But when planning meets robotics, often the part where it breaks is the complexity of the skills. And there's a lot where foundation models can provide, let's say, value in building these low-level primitives as well. Without these low-level primitives, our demonstrations or our demos for planning in robotics will remain very contrived. And I hope to see more interesting things from the community as this progresses. Thank you very much. I hope you have a wonderful conference. Happy to take questions.
All right, thanks so much, Animesh, for teaching us how to use program synthesis and foundation model for robot planning. In the interest of time, we'll take one quick question. Okay, maybe I'll ask one quick question. So I was just wondering, in the previous talk, Greg talked about how his work does planning under uncertainty. I was wondering could you share some insights how to model environment uncertainty or partial observability in the environment?
So I think partial observability is possible with perceiver models. Basically, whatever your perception system is will have a structured memory. So that your perception is not looking at what you are just looking at or an observation, but a system. So that way you can build what you would call unobservable systems or a memory of the system as well. Building explicit uncertainty is still something that is TBD, or uh, as far as I understand, there are no standardized solutions that work everywhere because these models don't give you very good uncertainty quantifications. However, as in most of these cases, we are not asking these pre-trained models to be the decision makers. They're only, let's say, generating programs or domains. In that case, what can be done is the predicate grounding, for example, in the work that I've talking about in Climb, the predicate grounding is where uncertainty will go in. So, for example, when you say, is the door open? That is actually going to be a classifier. So that thing is not a binary thing. It's a classifier. And that is where uncertainty will go in. And that is the part where you can actually make the process stochastic.